we're going to apply our knowledge of torque and what we already know about forces to solve some problems involving objects that are at rest, that is, in static equilibrium. And for an object to be in equilibrium, that means that sum of the forces is zero and the sum of the torques is also zero. And these forces could be in just one direction, the x or y direction, or they could be in both the x and y directions, depending on what the situation is. So really the principle is just that if an object is at rest and it's not moving from rest, and then some of the forces and some of the torques are zero. And so we just write out, in the x direction, we have a bunch of forces, or however many forces we have. In the y direction, we have however many forces we have. And then torques, we just write out all the torques that we have. Okay, so we're going to look through some different examples to learn some things. First off, first thing I want to talk about is balance. We briefly mentioned this when we talked about center of mass, but in order for an object to balance, like for example, if I go to hold this pen on my finger, then the center of mass has to be directly above my finger. If I move over here, now the center of mass is to the left of my finger, and that force of gravity on this pen we can treat it as though it's acting at the center of mass. And if the center of mass isn't above my finger, that means that the normal force, there's an upward normal force over here, there's a downward gravitational force over here, and that produces a net torque in this direction, whatever that might be, that will cause the pen to then fall, to rotate downward. So for an object to balance, center of mass must be directly above the support. Or if an object's hanging, it would be directly on the whatever it's hanging from. Right? So for example, let's say we have a mobile. A mobile is basically, there's a string attached to a stick, and then there are different things hanging from the stick. For the sake of simplicity, let's say we've got a meter stick. So this is a meter stick, and we've got a mass of 65 grams at x equals 12 centimeters. We've got a mass of 52 grams at x equals 18 centimeters. And then we have a mass of, 120, let's say 135 grams somewhere. And let's say the string is at 50 centimeters in the middle of the meter stick. So here we've got 12 centimeters. It's always helpful to draw a picture. 12 centimeters, we've got 65 grams at 18 centimeters. We have 52 grams. And then if this is, and we'll say this is balanced, which tells us that this mass is somewhere over here, but we don't really know where. We'll just say it's at x centimeters. And in order for it to be balanced, that means that the sum of the torques must be zero. And we can write out each of these torques. This one, from mass 1, we have the mg is the force, mg, and that torque is in the positive direction because it would pull downward, which would exert torque in the counterclockwise direction. And if that's 12 centimeters from the end, that means it's 38 centimeters from the middle. It makes sense to set our pivot point right here. So we go point times 0.38 plus 52 grams times 9.8, and this is 18, then that's 32 centimeters from that middle point, so that's 0.32, and then we have minus the third mass, 0.135 times 9.8, and you have to keep in mind that if x equals 0 is over here, then what we plug in here isn't x, but it's this distance from here, from the mass to the midpoint, which would be x minus 50. And so we can solve that to figure out where that mass would be placed for the ruler and we can punch those numbers in. We move that over, we got 0.065 times 9.8 times 0.38 plus 0.052 times 9.8, times 0.32. And that would be on the right side of this, so you move over to the other side, so it becomes positive, divide out 0.135 times 9.8, and then add, I wrote 50, but that's 50 centimeters, so it should be 0.5. And we can figure out that x is 0.8062, so that is at 80.62 centimeters from the end of the meter stick. It's worth noting that mass always the force of gravity on an object always acts at the center of mass. So if we have the same situation, we've got a ruler, and you've got a hanging mass, and I say this string now is attached at, say, I don't know, we'd have to have the hanging mass over here. X equals, say, 20 centimeters, and the meter stick has a mass of, I don't know, 75 grams. And then we want to balance things. We'll say we have a mass of 55 grams at x equals 0, and then a third mass of 120 grams somewhere. When we factor in the mass of this meter stick, again we're saying sum of the torques equals 0, and we have a positive torque from the 0.055 times 9.8 times, we're 20 centimeters away from, and we can set our pivot here again. Then you have to factor in the mass of the meter stick. And I just realized I wasn't thinking about this right. Make this one 120 grams, make this one 55 grams. So this is 1.120. When we factor in the mass of the meter stick, now the force of weight of the meter stick is it acts at the middle. So up here, the weight of the meter stick would act at the midpoint, which was our pivot point, and so it didn't supply any torque. Now, it's supplying a torque, and that torque is in the counterclockwise direction, which we call negative. So we have minus 0.075 times 9.8, and that's at the center of mass, which should be x equals 50 centimeters, so that's 30 centimeters, or 0.3 away from our pivot point. And then we also have a minus something, 0.055, 9.8, and we don't know how far away it is. Again, this is x minus, in this case, 20 centimeters. And then we can calculate what that distance would be, 0.12, 9.8, 0.2, minus 0.075, 9.8, 0.3, divided by 0.055, divided by 9.8, plus 0.2. And so we get 0.2272, or 22.7, about 22.7 centimeters. So we can work out where these things are balanced. I've put my pivot point here both times because that makes the most sense. It turns out that the math will work out regardless of where you put your pivot point. we can choose where we put our pivot point, and it'll work out regardless of where you put your pivot point. But if we choose our pivot wisely, and we choose it so that we eliminate torques, then we can make our problems easier. In this case, by putting our pivot at this middle point, we've eliminated any torque caused by the upward force of the string, so we didn't have to include this tension in the string into our calculations. So that made our lives somewhat easier. So there isn't a wrong place to put your pivot, but you can make problems easier by selecting your pivot wisely. Here's another problem that involves similar principles. Got a diving board that's attached in two places at one end and 1.3 meters from the end. The board is 3.0 meters long and has mass 110 kilograms. A person with mass 85 kilograms stands on the end and is about to dive in. Find the force exerted at each attachment. This is going to apply the principles of torque and force again. And once again, it is useful to draw a picture. We've got our diving board. It's supported at this end, and then a little ways in, there's another support, and we've got a person hanging out at this end. So it's a good idea to diagram what forces are acting here. We have, I'll call it N1, Fn1, normal from the first pillar. We've got Fn2, normal from the second pillar. We have the weight of the diver, force of gravity on the diver. And we also have the force of gravity acting on the board, which acts at the center of mass of the diving board. Now, we weren't given either of these. We have two unknowns, which means we're going to need two equations. And in this case, those two equations are going to be forces in the y direction and torque. So it's a good idea to set our pivot on one of these so that we can eliminate them from the torque equation. If I set my pivot here, and let's work out what our torque would be. Sum of the torques is 0. We have a torque from this guy, which is force times radius, and we said that's 1.3 meters. And that's a positive because it's counterclockwise. Both of these torques are going to be in the clockwise direction, so those are going to be negative. And we have minus the force of gravity on the board, which is 110 times 9.8. And that is acting at the center of the board. I guess I should have specified the diving board is uniform, meaning the center of mass is in the middle. The whole board is 3 meters long, so the center of mass is 1.5 meters from the end. And then we have minus the weight of the person, 85 times 9.8. And they're at the end of the board, which is 3 meters away from the pivot. And then we can work through that to figure out what this normal force is. In the y direction, the sum of our forces is 0, and that's a very straightforward equation to write. We have first normal force plus the second normal force minus the gravitational force on the board minus the gravitational force on the person. So we can solve this torque equation to get this force and plug it into the force in the y equation to get the normal force. So if I punch this in, when we move these over, they'll become positive when we move them to the other side of the equation. So we've got 110 times 9.8 times 1.5 plus 85 times 9.8 times 3. And then dividing out that 1.3. And so the normal force from that second pillar is 3166, etc. I'll store that as A. And then we can plug that in over here. Fn1, these two will be positive. 110 times 9.8 plus 85 times 9.8 minus that normal force that we just calculated. And normal 1 comes out to minus 1255. Well, what does that mean? It's negative? That might seem kind of weird, but what that means is that this attachment over here is actually pulling down on the board instead of pushing up on it. So I assumed it was pushing up, and that got me a negative, which means the force is actually going downward. So Fn1 is 1255 newtons down, and Fn2 is 3166 up.